Okay, so in the last class, we started discussing the 4-variable K-map, right? If you might remember. Um, Something's different today with the projector. I mean, anyways, is that so? Oh, are you guys all okay with this? So, okay, I don't know what's going on, but it's fine. So, so we practice with one example. We will repeat that very quickly, and we'll try one more example, and then we'll move on to the next one. All right. So the first example was this. You were given mean terms, of course, and as you know already, if you know the mean terms, basically you can just put in the ones in the proper position. So this is the M2, the second mean term. Excuse me. So it should be 0, 1, 2, should be right here. So the so 4 variables, you distribute them in like pairs, wx in one side, yz in the other side. So for this corresponding one, you should look for 0, 0, 1, 0, which is 0, 0, 1, 0 right here. Okay, let's do one more random example. So M10. So let's do 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is our M10. So it should be 1, 0, 1, 0. Let's see, 1, 0, and 1, 0. So right here. All right. And you'll get some more practice for, in homework 2. Homework 1 doesn't have K maps. So just, wait and see how that next one comes in. But meanwhile, you can also do some random practice at home. So assuming that we go through the list and put in all the ones in their proper places, we end up with this K map. And now we have to group them. All right. So as I told you, and as we experienced together, the more ones you can group together, the easier the expression will be. And today we'll talk about the possibility of having multiple grouping options. And all of them will probably appear good, but you don't know which one to take. And hopefully by the end of this lecture, you'll learn the process of choosing the best possible option. Okay. So before that, we are just oblivious to the fact that there is a way to choose the best possible solution, right? We are just doing it based on the feeling. So my feeling is if I group these 4 ones together, it's probably going to be good. Okay, the more we can group together, the better it is. And then I can group these 2 ones together, and the other 2, this one and the other one, can also be grouped, right? Let's do it quickly. And we are doing it just for the sake of practice, folks, right? So that's why there are multiple examples. So please participate in it so that it's less confusing when you get home. So let's start with the bigger one, this one. We have, let's see which variable doesn't change. Yes, thank you. So first of all, this z doesn't change because as you can see, it is 1 every time. So I will start with z because you have 1 corresponding to it. You don't have to prime it. For the other case, in the other direction, x doesn't change. You see that? So, and it's also 1. So xz is one of the terms. So we covered this. How about this one? What doesn't change here? W and z doesn't change along this column, right? And both of these are 0. So I should prime them. Y prime, z prime. But is that it? Or do you have any other variable that doesn't change? W doesn't change. And W has 1 corresponding to it. So I should just write W. Are you good? The only thing left now is this one. Which variables don't change? Y and Z don't change. So Y and Z prime. And then there is another variable that doesn't change here, which is X. But you have 0 corresponding to X. You should write X prime. There you go. Okay, so we looked at this example before. I'm not spending too much time here. Let's move on to a new example that we didn't see before. All right, guys, ready for it? Okay, let's try to, I mean, obviously we have to go through the list and distribute it into the truth table and then put it back into the K-map, right? I'm just gonna do one example without any loss of generality. Let's take, I don't know, say M5. It's like 0, 1, 2, 3, 4, 5. So that's where you have a 1. Corresponding to that, you have 0, 1 and 0, 1, which would be 0, 1, 0, 1. So right there. And you could distribute the rest, right? One easy way would be if you see too many ones, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Notice something, folks. There are 12 ones in here. How many zeros? 4 zeros. So I suggest you look for the zeros and put the zeros in and fill the rest with ones. Does that make sense? That's why I chose this example. Sometimes people, especially during your exam, you have to make a call. If yeah, this is the right approach. You could just go through this, find all the ones, and then put them back in here. But if you instead look for the zeros and put the zeros in place and fill the rest with the ones, it will be easier for you. And for the sake of time, I just did it before. And there you go. You see, it's almost full of ones. But if I had gone for zeros instead, I could have filled this 4 positions, and then the others could be filled with 1 quite fast. Does that make sense? Logical? All right. Okay. Either ways, you are getting this K-map that has many ones. And this is where I start showing you the multiple possibilities. First of all, when I try to group them, I'm getting rid of the zeros just to make it a little bit more clear. So there are many ways to group them, and I'm kind of confused as to how to do it. First of all, we can group these 4 ones or these 4 ones. And let me show you one option there with a different color. Just look at this 1, 2, 3, 4 ones. You see that they're basically adjacent to each other, right? Because K-maps wrap around both in horizontal direction and vertical direction. So this one is a neighbor of this one. And both of these are neighbors of the other 2 ones. So apparently these 4 could be grouped together. And the more you group, the better it is. You can group 4 of them. Okay. And by the way, when you're doing horizontally, you are grouping 4. When you're doing vertically, you are also doing 4. When you do it this way using a rectangle, you're also doing 4. So that's how you can cover all the ones. Does that make sense, folks? Or no? Now, sometimes people can be confused, and I have, yes. Absolutely. Absolutely. Yes. So you are heading in the right direction. You're also already indicating to the algorithm, right? So basically, so there are different strategies of covering all the ones. First of all, we have to cover all the ones to be functionally correct. At least the function will be correct. But will it be optimized? That's a different question. To make sure that function is also best possibly optimized, you have to make sure you don't really repeat the ones too many times. Okay, if you just, yeah, I can take this one or the other one and the other one. Notice you're covering this one 3 times already. Right? May not be the most efficient thing to do, but I don't know. We'll see. So we have to find a strategy, and I haven't taught you the strategy yet, so I'm not commenting on that. I have a separate slide that tells you the possibilities and how to pick the ones that you're eventually going to go with. Okay, until then, because we are all on the same page here, I don't want to go forward and show you, hey, here is how you should pick it. But feel like as at this point, it's fine. Just try to make sure that you cover all the ones and try to minimize if possible using your common sense logic, not any algorithm because we don't know one yet. Just using your common sense logic to not repeat the ones too many times, right? So let's try to do this. I think doing this 4 ones simultaneously will make a lot of sense to me. And then it looks like merging this 4 will also help. But then one more thing that I want to do is, give me 1 second. Let me use a different color here. Okay. So notice this one and the other one, they're also adjacent, don't you think? And finally, I have 1 left right here. I could just group it with one of these ones. I mean, no matter how I do it, at least one of the ones will be repeated. You see that? Yes. Could you repeat that? Sorry. Right. Yes, exactly. You could do a horizontal like I was trying to draw initially. You could definitely do that. Nothing wrong with it, honestly. But my question is, how do you do? Like, how do you choose? Should I go with this approach? Should I go with the horizontal approach that we discussed and you mentioned as well? So we'll learn that soon in a few slides. But you're right. You could do that as well. Yes. This one with the one on the bottom without any any real reason, honestly. Let me show you. I could have grouped it with this one or the other one because I have to cover this one for sure. Oh yeah. Oh, I'm sorry. Yes. You're right. So you caught it. Yes. So these two, right. That way we don't have to repeat it. So I missed this one. That there was another one sitting right here. All right. Any other question? There was another hand around here. Yes. Oh, okay. So thank you. I think both of you caught this same issue. Thank you so much for catching it. I kind of missed this one. This guy was sitting right here, right? Okay, that's great. So that means we have 1, 2, using different colors will be better. 3 and 4. 4 groups. There you go. You could just go ahead and, spell out the function now. Are you guys all with me so far? We'll just try spelling out one because I mean, for the interest of time, I don't want to go through the entire thing. And there are other things to practice, by the way. So I'm going to do just one. Let's do the one that we missed. Okay. Let's do this one. This one. What will be the corresponding term for this one, folks? Which variables don't change? YZ. And both of these are 1. So YZ, no prime, by the way. YZ. What did I do? And then there is one more thing that doesn't change here, which is X. Thank you. But X has 0, so it should be X prime YZ. So I covered one. And then there will be others as well. We are not covering that. You can try at home. Now, let's move on to the new concept, because like I said, there will be many K-maps coming up. We don't have to necessarily go through all of them. But the concepts are important and they will build on top of each other. And the way I design them is to make sure that you feel the limitation with the previous approach, or you feel hopefully what you don't know. Because I mean, somebody told me, and I think this is a very famous quote, the best thing to understand is what you don't understand, right? If you understand that I don't really know this, then hopefully you can find a way to study. Okay, so one other quick thing to see. Notice all of the functions that we're getting out of a K-map are SOP, sum of product. If you notice that, this is essentially a sum of multiple products, right? So SOP form. But what if I want to get a POS form? Product of sign, product of sum form. Have you ever thought about it? There could be a question. For some reason, I need product of sum. But how can I get it? Yes, you're right. But K-map requires that you group the ones. So that goes against the K-map principle. However, but you cannot change the functional output, right? Because if you only group the zeros, the functional output will be, wait for it, exactly inverted. So if you go for the ones, whatever function you get, if you go for the zeros, you get the exact opposite of that function. So instead of f, you're going to get f prime. Are you all with me? So I'm going to go for that first. And this is an interesting strategy, which I think you should know. So imagine you have a K-map. Somehow you get this using the function truth table. Somehow you get this K-map. So instead of going for the ones, you're now going to go for the zeros. You see that? It's already done for you. So you go for the zeros. Interesting kind of K-map, right? Now, if you group them together, you basically get the function. Yeah, let's do one together. So which variables do not change for this one, folks? Yes, yz don't change. So we need to take y prime z because y has 0 corresponding to it. So there you go, y prime z. And which other variables don't change for this one? W and x. And both of these are 1. So W and x. But there's another variable that doesn't change, z, but prime. Yes, thank you. Sorry, I'm getting ahead of myself. Okay, the final one is this one. You have w prime xy corresponding to it. Okay, so you arrive at this inverse of function f, but you really want function f, not the inverse of it. Okay, so how can you get it? I'm going to show you the shortcut first, the easier way to get it first, and then the actual way you arrive at it. So notice, if you get this sum of product for f prime, and you try to get the product of sum for f, this is how you can get it. Just take a look at this, each one of these terms. You notice that y prime z, it's a product. You convert it to a sum, but you invert every literal. So wherever you had y prime, you make it y. Wherever you have had z, you make it z prime. I'm telling you the shortcut first without the logic, okay? But then I'll show you how to get it. Okay, the next one, it was a product term. I'm going to convert it to a sum. Just add the literals and invert them. So instead of w, I have w prime. Instead of x, I have x prime. Instead of z prime, I now have z. And the rest. And instead of the sum, you make it product. If you learn it as a shortcut, would you be able to do it? Right, just as a shortcut. Can you do it? Is it difficult? So after you get the sum of product for f prime, you could easily convert to f and get product of sum. Okay, now how do you get it? And I added a short note here. You use De Morgan's law. Remember, when you take prime of this function, you get f, the actual function. Does that make sense? So when you take prime, you have to take prime here in both ends. Are you good? Okay, now you could treat it like basically two terms, a and b. So what you have here is a plus b whole prime. A plus b whole prime is actually a prime and b prime. Okay, so basically De Morgan's law. So if you, and by the way, and then you have to keep repeating it for the two terms here that you grouped into one terminologies, right? So if you go down the rabbit hole, you just keep doing this calculation, at some point you end up with this. So I have it as a homework for you to just have a feel for how to calculate this using De Morgan's law. You just have to keep repeating it, that's all. It takes like 6-7 lines of calculation. So that's why I'm not repeating it for the interest of time, first of all, and real estate, because it will take some space to write. And when you work on the homework problem, if you're stuck, then come talk to me. I'm happy to work with you on this. But give it a shot. I'm sure you're going to get it. And the hint is right here. Just keep applying. And I've already told you how to start. Start by grouping them as one, and sorry, as A and the other one as B, and then move forward with it. And then finally, you have to take it out as well. You will see you arrive at, and these are the exact two functions that I added for your homework 2. The same one. So you can compare whether you get these output from the function that you're given. Sounds good, folks? Okay, but at least you know the shortcut, and you also know the reason. Basically, it's not really a shortcut. You just keep doing the math, and people realized, oh, okay, it could be shaped into a shortcut, and we could just use the approach in a generalized format without having to go through the calculation all the time. Okay, so this is an interesting neat trick to get product of some form. Remember, I mean, just take a step back and try to appreciate the fact and as to how powerful this is. Remember in the very first few lectures, when I gave you a function like this, so if I gave you this function instead, the product of sum, and I asked you to get sum of product, you could have easily just multiplied everything, reduced it down with some Boolean algebra, and then get the sum of product. Isn't that so? But if I gave you product, like sum of product instead, like this one, and I asked you to get this, that was very difficult using functional approach. But remember, the first thing that we learned in this course was using Boolean Boolean algebra to do things like that. And I told you it's really complicated, and it's not really straightforward. And I could show you in a slide that here is how you do it, but that's not how real life works, because I don't have the solution in front of me. You could keep trying these and that and this, and it will take you an hour maybe to arrive at, depending on how complex that things are. Okay, and you don't, if you don't know this beforehand, if it is not given in the solution already, so it was not really a viable solution. But at some point, that was the solution. Remember, Boolean algebra goes back century, right? But K-map goes back to like maybe 50, 60 years. So it was after decades of excruciating pain that people went through to optimize Boolean stuff, then they realized, hey, we need a better approach. And then K-map came in. So just imagine you are the person proposing this new approach. Just imagine the impact on the community, right? That's how things work. People suffer for decade is a long time, maybe, right? Decade is a long. My career is not even probably a decade long yet, a faculty career. So just imagine, decade is a long time, and when it takes like 5, 6, 7 decades to get a better solution from the conventional Boolean optimization using algebra, you appreciate it more. It's like a lifesaver for the engineers. For the engineers, imagine you working for a company with just Boolean algebra and trying to optimize these functions from this to that, right? You'd be really appreciative of K-map then. Okay, all right. And by the way, K-map is not the end product, and hopefully that's my story. That's the story behind the lecture. By the end of the K-map lecture, you realize that this is not enough. Okay, so I'll leave you with a notion that, hey, we need more, and there will be other approaches coming in. Okay, so move forward to the next point. This slide will show you, and I already indicated that there are different ways of grouping the ones. There is not just one way. There are multiple ways you can cover all of them, but which way should you choose? So this is taken from the textbook again. We will learn the concept of prime implicants. Okay, what is the prime implicant? So every time we take a group of one, that is an implicant, that is called an implicant. Okay, like for example, this group of 4 ones is one implicant. Imagine if I had just one sitting here, say, just one. I mean, this is not an ideal example because I can group it with the other one. But for some reason, you chose to group this one separately by itself. Okay, for some reason, maybe there is no one here, say. This single one would have been an implicant. Okay, does it make sense? An implicant doesn't necessarily need to be a group of multiple ones. If you have to take it, you have to take it. It's fine. If you have to take a one separately just by itself because it cannot be grouped to anybody else, sure, it is what it is. That is an implicant. Are you all with me? Okay, so how many implicants are we looking at in this diagram? This is one implicant. This is another implicant. Like if you take groups, this is a possible implicant. This one with like wrapping around, this is another implicant. So there are multiple implicants here. Are you all good? Yes. Yeah, so alternatives, of course. So you can find alternative ways to cover the ones. And in doing so, you end up with different implicants. So we are using technical terms here, by the way. Initially, I didn't even tell you what the implicants were, but you are using implicants, weren't you? You are using implicants. You are using them to convert to function. Just didn't know the term. I'm just giving it a name now because we are going to learn about prime implicants. But before that, you need to know what implicants are. So you have been already using implicants. Does that make sense, folks? Okay, we have been using implicants all the time. Now, what I want to show you is for example, to cover this particular one, notice just one of the examples, just to cover this particular one, I could either choose the horizontal option and group it with the other one, or I could choose the vertical option and choose group it with the vertical one. Doesn't matter. Either ways, you're covering one. I'm not going to do both, obviously. I'm going to do one. You can do both and still be functionally correct, but you'll not be optimized, as you can already hopefully appreciate by now. And there are questions, and I really like the fact that when you discover it yourself that, hey, should we be covering the same one so many times? No. If you don't need it, you don't do it, right? You cover only once if you can. If you absolutely have to, then you repeat it just to make sure you cover another one, but not for the sake of repeating it. That, hey, I want to do both horizontal and no, that's not optimized. Okay, now, but you see, your friend might pick this implicant and you might end up picking the other implicant, and apparently your functional representation will be different. I hope you can appreciate that now, right? The function f will look different. It becomes challenging for me to test if I give you a test to like optimize the k-map and you choose different implicants and your functions will look different. I cannot just write a solution and compare. Does it match? No, I have to basically carefully check it, right? Okay, so what I'm getting at is a function has many implicants. If you see, now you all understand what implicants are, right? Okay, now I'm gonna use the term prime implicant. What does that mean? I'm gonna draw on top of this figure. So please pay attention because it's gonna get messy quickly, okay? So imagine for some reason, somebody chose to take this as an implicant. Okay, this two grouping together, it's an implicant. It's a valid implicant, no doubt. It may not be the optimized, of course. You can group more ones, but it is an implicant. It is an implicant. Okay, but notice this implicant could be easily covered with a bigger implicant. You see that? So this red implicant that I just drew could fit within the yellowish one. So this red implicant is not a prime implicant. It is just an implicant. But the yellow implicant that I drew, you cannot have another implicant covering the entire one. It can cover a portion of the ones, but not the entire implicant that you have just come up with. Does that make sense? So this yellow implicant, I don't know if you can see it, or maybe I should use a different color, maybe red. This red implicant that you see here is a prime implicant because it cannot be fully covered by another implicant. Am I making sense here, folks? So in fact, all of the implicants that you have seen here marked, all of the implicants, all of them, they are all prime implicants because you cannot show me a single one that can be fully covered. Even this one, notice, even this one. Can you give me one implicant that fully covers this one? No, you can have two, like 1 and 2. Together they cover that implicant, but not just one implicant fully covering that. So that's why even this one is a prime implicant. Are you all good so far? Okay, now let's try to come up with the minimum solution of this function. Let's do it. Okay, let's work together on this. So let's take this 4-1 groups first. And let's try to make it quick this time because, hopefully by the end of this lecture and the next, you'll be like really efficient in doing K-maps. You don't have to wait too long. And I see that you have already developed quite a lot, right? So which variables don't change? Let's start with B. And corresponding to B, you have 1. So you're just gonna leave it to B. And how about this two? What doesn't change here, folks? C doesn't change. So you have C prime or BC prime, whatever. So notice you have BC prime. Okay. I will stop when I cover all the ones. That's when I stop making the function. Okay. So I've covered these 4 ones. Let me just mark it here. I've covered these 4 ones. And then I'm going to next cover the other 4 ones. This one. This one. Let's do it together. A doesn't change between these two. So you have A. And then what else? C and D. C doesn't change, right? So you have C, AC. So you have AC. BC prime plus AC. That's what we covered already. What is left? Only thing left now is this one marked with green ellipse. So let's do it together. You have A and B that don't change, and both of these are 0. So A prime, B prime, and something else that doesn't change is D, and this is just 1. So A prime, B prime, D. So this one as well. Notice with these 3 implicants, which are also prime implicants, by the way, with these 3 implicants, you have covered the function. Are you all good? But wait, I can have other implicants. I can have these 4 ones grouped together. I mean, the argument is the more you group, the better it is. Sure, I'm grouping 4 here and this 4 here as well. What is the difference, right? Are you guys all with me so far? So you have the equal number of ones being covered, either horizontally or vertically or in a square fashion. You're covering 4 ones. So essentially they should be the same. But then you don't really need to group them this way. You can group them using the square as well. So if your friend, instead of going through this route, like grouping 4, 4, and 2, if somebody started with this vertical 4 and then tried the other things and covered all the other ones, you'll end up with completely different functions, of course. But how do you know who is more optimized? That's first question. Do you see the dilemma now or no? Okay, you see the dilemma. And what I want to show you is, yes, the implicants that we used, we could cover the function with just 3 implicants. But there are other implicants that you see here marked. These are other implicants. And all of these are prime implicant, by the way. And this, I mean, just imagine, let's start with this one, this 4 ones grouped together. Let's do it. What is the corresponding functional outcome? The variables that don't change are A and B. And then is there anything else that doesn't change? No, everything else changes. So AB, notice AB. We never used AB. Good? Okay, so notice these blue ones, the ones that you see here, they're all prime implicants and they're, marked here 1, 2, and 3. These 3 prime implicants have not been used to make the function. So simply because an implicant is a prime implicant doesn't mean it will always be used or it will always show up in the actual function. Are you all good? First of all, implicant. You have many implicants in a K-map. Not all of them are useful because some of them are prime. Like if it is not even prime, forget it. Because if there is a prime implicant, it will cover everything, right? Okay. So prime implicants narrow things down even more. But among the prime implicants, not all of them will show up in the actual function. So the ones among the prime implicants that will show up or should show up in the function, they are called essential prime implicant. So implicant, prime implicant, essential prime implicant. You see the hierarchy here, folks? Okay, so I'm heading into the next slide. Any confusion? I'm not in a rush. Okay, it is important for us to understand this properly. All right, so before moving on to the essential prime implicant slide, I think I already made the point, but still I had another example in a slide to show you, why it is necessary for us to think of a structured way to choose the prime implicants. There are 7 prime implicants. I'm going to take like 3, but which 3? It cannot be just based on random guess, right? You see my point? Okay, so hopefully it will make sense. But now, so on your left and right, you're looking at the exact same K-maps. And based on how you group them, you end up with different functions. We are not going to work on it together in the class just for the sake of time, but this is right here. And I hope with the amount of practice that we have had together as a group, you can easily deduce it yourself. So using this type of grouping that was chosen for you, you end up with this function. And with this grouping, you end up with a different function. And notice, and the point that I'm trying to make is, yeah, you can end up with different function, nobody cares, as long as both of these are optimized. And how do you know both of these are optimized? How many AND gates you are using? How many OR gates you are using? And if you're using the same number of AND gate and OR gate, are they all of the same input type? Like, is it 2 input AND gate or 3 input AND gate? Okay, let me show you. So here you're using 2 input AND and basically 3 of them. And then an OR gate with 3 inputs. Does that make sense to you, all of you? Okay, but here you're using 4 2 input ANDs and a 4 input OR gate. Obviously, I don't have to tell you which one is more optimized, right? Okay, and even by looking at the function, you can tell that there are more terms here, so it's definitely not more optimized. But you did the right thing. You covered all the ones here. You just group them in a different way. That's all. So we have to be mindful. So K-map is not the final solution. Oh, we have K-map. We know how to cover all the ones. So it's optimized now. Even within it, there are additional considerations. So that brings me to the next slide, where we should learn about choosing essential prime implicants, the ones that are essential and you cannot live without them. Ready to learn now? Okay. So the way you choose essential prime implicant would be by looking at the ones. If they, trust me, it's not possible to find out all that are essential. There will be some that are optional, but you start with the essentials first, and then you leave it for the choice. So first choose a one that can only be covered with one implicant, if there is any such ones. Okay, so obviously I have the privilege of pre-choosing the problems so that I can explain it to you in a timely fashion. So I chose this problem, of course. Notice this one. In fact, the ones that are marked with this bluish shading, all of them can be covered with just one implicant. Notice that. I want to use another technical term here, folks. Each one of these ones is called a min term. You guys remember this? We covered it together. I mean, if you don't know what I mean, notice what were this? Lowercase m represents min term, uppercase x represents max term. So all of the ones that we were putting in the truth table, they're basically min terms. So in your textbooks, they call the ones min terms, every min term. And I'm telling you, every one, they call every min term. So it's all the same, okay? So basically, if a min term is covered by only one prime implicant, that prime implicant is called essential. Okay, so basically look for the one like this one, which can only covered with a prime implicant like this. You can see that? Give me one more time. So can I group this three together? Can I? Can anyone tell me? No, remember, you can only group number like in terms of power of two. You can either do 2 power 1, which is one, just one of the ones, or you could do 2 power 2, that means 4, and 2 power 3, that means 8. But you cannot group 3 or 5 or 7, right? So just be mindful of it. Simply because there is more one, you cannot just group them. Okay, so you can only do this. And notice, is there any other implicant that could cover this one? Can you find any other implicants here? No. Okay. How about this one? Of course, I looked at each one of them. I mean, and we could choose, hey, this one cannot be covered with anything else. So this is another example of a one that cannot be covered with any other prime implicant except for the one that we have chosen. Okay, one question. Don't be confused. Let me show you one more thing, because I get these questions a lot. First of all, hey, this is an implicant that covers this one. Don't you think? Let me use a different color now. The red implicant, okay? Let me use a color like green. The green implicant can also cover this one. So the same one can be covered with multiple implicants. So remember, I don't know if you heard, that's why I'm giving you this example. I told you, if this one cannot be covered by any other prime implicant, not implicant, prime implicant, do you think the red one or the green one is a prime implicant? No. Why? Because both of them could be engulfed by this square-shaped bigger implicant completely. So neither of these, the red one or the green one, are prime implicants. They're just implicants. I told you that if there is a one that could only be covered with a prime implicant, just one prime implicant, that is an essential one or essential min term. And the implicant that can cover it is an essential implicant, essential prime implicant. This one is an essential prime implicant. This one is an essential prime implicant. And what else? Notice, to cover this one, you could have only this. So this is another essential prime implicant. Are you good? Any problem? So notice, just by choosing these three essential prime implicants, by the way, okay, let's convert them into functions now. Let's start with the square one. Can you help me do it quickly? Which variables don't change? A doesn't change. You see what I'm going with here, folks? First, this square. A doesn't change, so you have A prime. And what else doesn't change? C doesn't change, so C prime, A prime, C prime. If you do the second one and the third one, you get the other two terms, okay? So apparently, you have covered all the prime implicants, essential prime implicants, this one, and this one. But there is just one of the ones left. You see that? The essential ones have covered most of the ones, but you have this one sitting in here. Now you have options. Now you could either group it with this one or the other one, doesn't matter. So corresponding to which one you choose, horizontal or vertical, you either get this or the other one. So your functions will look different. But you can only start choosing randomly after you have covered all the essential prime implicants. So the strategy is first identify the essential mean terms, essential prime implicants, and take the prime implicants already and see which ones are left. And the ones that are left, you could then cover them somehow with these or that, and that's acceptable. You're going to end up with optimized solution. And notice they look different, but they're both equally optimized. So you have three inputs, same. Not the same inputs, of course, but you have the same cost in terms of hardware. Are you all good? Okay. So essentially, all of these are mentioned here. You can just read it at home if you want to. Okay. So that's an interesting. And by the way, when we code them, when we use software to code this, we write a code to basically there is an algorithm in the textbook. If you want to, if you're curious, just take a look at it. The algorithm doesn't show you the code, but you can convert it to a code looking at the algorithm. Okay, so the algorithm shows first step would be to choose the ones or look for the ones that could only be covered with one prime implicant, and then choose those basically what we just discussed. So when we come up with a strategy, we could convert that strategy into an algorithm, a flow chart, and then you can convert it to whatever language, a programming language you want to convert it to. Yes. Question? No? Okay, sorry. All right. So an obvious question. Did I tell you about don't care conditions? There are situations, and we will see some of them. And in fact, the next lecture will begin with such a like practical example that you'll use in this course in your lab actually, right? Don't care. So there are some Boolean functions in truth table where some combinations could either be 0 or 1 in terms of functional output. We don't care. And basically, as the name suggests, we mark them as don't care conditions. Okay. So how do you handle don't cares in a K-map? It's easy. Just listen to me, we'll be in good shape. So notice this is a function. You have the min term, so this will be 1, and you have a set of don't cares. That's how we represent don't care functions with don't cares, right? Okay, so you distribute the ones in the K-map as well as the don't cares. Just keep them separate and see if you could use this don't care. If you consider this don't cares as 1, they may help you group more ones together. Okay, so imagine if I considered this don't care as 0, then I could have already grouped these two ones, and this could be separate or it could be grouped with the other one like this. But will it be better, or will it be better if you group 4 of them together? By now, you know, the more you group, the easier the expression becomes. Don't you think? So if I consider this don't care as 1, it is beneficial for my optimization. So I'm going to consider it as a 1. Okay. And the next one, how about this? If this was 0, I would never be able to group these 4 ones together. I could only do this 2 and this other 2. But when you consider it to be a 1, you can group this in a bigger structure. Okay, so you just take the don't cares that help you group more ones together and consider the others as 0. So this is an example. After you group them, just treat it like 1, done, and do the rest. You have had plenty of experience already, so I'm not repeating it. What I'm going to show you again, this is the second example where you don't use all the don't cares. So this is taken from the textbook. The other one is just made up. This is taken from the textbook. In your textbook, they use X to represent don't care. Okay, some other textbook use D. Doesn't matter. So whichever, it will be mentioned. X is don't care. Okay. So basically, this don't care condition helps you group 4 ones. Oh, by the way, if you are confused with this notation, 1, 4 represents 1 at the location that represents 4, right? 4 is 0, 1, 0, 0. So what is 0, 1, 0, 0? 0, 1, 0, 0. So that's the fourth position. That's why. Okay, just don't get confused with it. Essentially, these are all ones. So if you consider this don't care as 1, you can group 4 of them together. Sure, I will take it. And how about the other X? This one and the other X. I mean, do you really need to cover it? No. If you consider them as 1, you can cover it again, but you don't have to cover that don't care, right? So you'll be creating a new implicant just to cover this don't care if you consider it to be a 1, which I don't want to. So I will treat it as 0 and forget it. See, all the ones are covered. I only consider this don't care as a 1 because that helped me group the existing ones. So I only think about the ones that are really 1 and convert the don't cares that help the ones get a bigger group and ignore the ones that don't. Does that make sense, folks? So don't cares make your job easier. You have the option to create bigger groups by converting them to 1, or you have the option to just ignore them. Okay, so this is definitely not a problem. It is a better, it's very advantageous to us. Are you all good? Okay, yes.
So I show that as a don't.
So that's a good question. So I should have probably converted. There is no difference actually. So after you decide which ones to keep 1, you no longer treat them as don't care. Just convert it to 1. Like you don't have to convert it, but in your mind, convert it to 1. So nothing changes. Okay. So we just have one slide left, which I'm not going through today. I know we have 1 minute. I just want to show you what it is. Isn't it logical? After 4 variables, what do you have? 5 variables. So the last slide will do 5 variable K-map. And this is intended to show you why we cannot keep using K-map because it becomes so complicated after this. You see, so this is the intention, right? 5 variables typically where we stop. You can do 6, 7, fine, but we don't do it. All right. So in the next class, we'll start with it. I'll assume by then you'll have like plenty of experience with K-maps. I'll not repeat it too much. Okay. Thank you.